So far, we've talked about the relationship between force and displacement, or stress and strain. We've talked about a linear elastic material, meaning that force and displacement are linearly related. So in this video, I'm going to show you some real material behavior, and we'll talk about the implications for engineering design. So here's a typical metal plotting stress versus strain, or more specifically, engineering stress versus engineering strain. If we remember, stress was force divided by area, strain is change in length divided by length. And since the area and the length change throughout the course of an experiment, engineering stress just means we're dividing it by the initial area, and engineering strain just means we're dividing by the initial length and not worrying about the fact that the area and the length change. So we see a few things on this diagram. First, we see a nice linear regime here between stress and strain. So we do see that at least for small values of stress and strain, the linear relationship actually holds. And that's this expression here. E being Young's modulus is stress divided by strain. So this diagram, they're using S and E for stress and strain. This point here is called the yield strength, and this is the point where the material begins to what we call yield or permanently deform. So up to this point here, the material behaves linearly, and if I pull on it, I go up. If I let go, I return back to the initial place. The material doesn't permanently deform. Once I kind of cross over this point, what can tend to happen is when I release the load, I fall back down on another line, meaning that I don't return to the same point that I did. So now the material is deformed permanently. If I continue to increase the stress as I go up, it gets higher and higher and higher, and at some point I reach what's called the ultimate strength, or the maximum stress that this thing can hold before it snaps. Now the behavior here gets a little bit unusual, because what can happen is if the material is very ductile, it will tend to neck, so it will start to close in. So in this case, that now the area, the stress could be increasing in a true sense, but in the engineering sense, we're dividing by the initial area. So there can be this kind of funny decrease we see here, and then at some point, as we keep pulling on the material, eventually it breaks. Now in our course, what we're always going to be interested in is in the behavior in this regime over here. We are going to always want to avoid this kind of point here, because we don't want to build a bridge that permanently deforms and the driver looks out and sees a bunch of bent truss beams. So we want to operate very safely in this linear reversible regime. So all of our analysis in the rest of the course is going to go here, but understanding what happens at the higher values of stress is important. So here we're looking at, again, stress versus strain for different steels. So these are all nominally the same material, but we see quite a wide variety of behavior. So all these steels have essentially the same modulus of elasticity, so the linear regime all follows kind of a similar behavior, but once we start to yield and plastically deform, the behavior can be quite dependent on the details of both how we treated or processed the steel and how much carbon and kind of other elements we've put in the steel. So we see quite the range. So here, some of these are reaching up to 1,000 megapascals before they start to undergo plastic deformation, whereas some of these here, it's somewhere around 250. So maybe a factor of 4 or more in terms of what the yield strength is, even if they have the same modulus of elasticity. If we look at typical values of the modulus elasticity for metals, we find they typically group mostly in the ballpark of around 100, at least that order of magnitude. Now, of course, we see some that are low, like lead, which you might have some familiarity with. It's quite soft, it's one of the lowest. Here, steel at 200. Tungsten is one of the hardest at 400. So, but we do see there is quite a grouping in the metals typically fall in this kind of range. So in a little bit, I'll show you a full scatter of what the modulus of elasticity can look like for a wide variety of materials. Here we're comparing steel to aluminum. We see qualitatively similar behavior, but again, the orders of magnitude can be quite different. So here we see this 280 here is a little after that, somewhere between 280 and 420 is when this one starts to curve over. With our steels, we see them typically quite a bit higher. And we see the axis here is quite a bit different, right? So 560 is the maximum to 1400 in terms of megapascals. So the steels can withstand typically quite a bit higher load. And if we looked carefully at the slope here on the stress strain curve, we see here this is 280 versus 4. So the slope here is about 70 versus 200 that we see with the steels. But qualitatively, we see the two behave quite similarly, so we see a lot of the same features. If we look at brittle materials such as glass or aluminum oxide, we see something quite different. So now all we see is a linear regime and nothing. So glass is a brittle material, so it follows this linear regime, and if we exceed the maximum stress, the glass just shatters, it just breaks. Another behavior that can be a little bit unusual is materials such as concrete or stone don't act the same in tension or compression. So concrete is typically used in compression, and we see here, since concrete's used in compression, they've put positive strain and stress kind of plotted in the way we would normally think of it, but they flipped it around. So here is the maximum compressive stress. Here is the maximum tensile stress. So we can see quite a bit higher. So this would be pretty typical of concrete, that it has the same slope here, right? The relationship between stress and strain follows the same slope when the loads are small, but how far I can push this in terms of compression is much, much higher than what it can withstand in tension. So these are some really interesting diagrams. I'm going to show them briefly, but for you to understand them, you're going to have to dig into this much more deeply on your own, and we'll kind of review this in later lectures too. But for now, I'm just going to kind of show them briefly. So these are diagrams that are often called Ashby plots. The reference is down here, so you can look at some of these on your own. And what they do is they take two different material properties and kind of plot where different classes of materials fall. So this is looking at Young's modulus versus the material's density. So we see generally kind of a correlation here, that things with high density tend to have high Young's modulus. Since this is a logarithmic scale, you should note that this is quite the range of values. So if we look at something like our polymers and our elastomers, we see that they cluster with their density at around 1, which in these units would be the density of water. Here's wood, which is a little bit less dense than water, so it floats. But we see quite the range here in Young's modulus. So our elastomers, which are nice and soft and squishy, polymers that tend to be more rigid are quite a bit higher, right? Because this represents 5 orders of magnitude going from bottom to top of this blue regime. We see our metals out here. So our metals typically have pretty high Young's modulus. We see a lot of overlap with the ceramics as well. The ceramics and the glasses tend to overlap in terms of what their modulus of elasticity is. And in some cases can be even quite a bit higher. And again, so here's steel here at 200 in terms of its modulus elasticity, 200 gigapascals. The aluminum alloys are down here around 70 gigapascals, which tend to be the same order of magnitude as the glasses, which tend to be maybe around somewhere between 50 to 100, depending on the exact type of glass. But this is modulus versus density. We can also look at modulus versus strength. We see kind of a correlation here, except you have to remember this is logarithmic, so it's quite the scatter. We see the elastomers sitting down here kind of on their own with a very low modulus, so nice and squishy, even though their strength isn't all that bad. We see again this kind of overlap between the metals and the ceramics. So the metals typically having the highest strength, but many alloys and many metals having kind of an overlap with the ceramics. Here's glass here, so not quite as high as some of the stronger metals like our aluminum alloys or our steel alloys, but still pretty good. And you can see kind of large regimes, right? So here the aluminum alloy is shown as this kind of elongated ellipse, meaning they all typically have very comparable Young's modulus, but the strength can be quite different depending upon the exact alloy and the exact processing conditions. And the same thing with the steels. And we saw that on one of the previous graphs where I showed they all have a very similar slope in the linear regime, but they can have very, very different behaviors in terms of what the ultimate strength is. So let's look briefly at a comparison of a couple different materials. So these are just going to be sort of hypothetical ones. So we're going to have a nice linear elastic regime here, and then this kind of behavior like that before the material fails. So that might be something like aluminum. Something like glass follow kind of a not so different slope, but maybe a slightly lower strength before it just breaks and sort of brittle fracture. And an important thing to understand here is the difference between aluminum glass is not so much this difference here, the difference in the strength, but the area under the curve. By that, I mean the area under the stress-strain curve. So what does the area under the stress-strain curve mean? So let's return to our example where I have a simple bar of length L, cross-sectional area A, being pulled on both ends by a load P. And what we're going to do is we're going to start off with a very small load, and I'm just going to keep pulling on it with an increasing force until this thing breaks. And so what that's going to do for us is create a diagram where we increase the load as a function of displacement. If I have my metal, this might bend over, and then we break. And so we want to understand what the area under the curve represents, because I just told you that that was an important measure. So let's go back to our definition in physics of work. So you probably remember some expression that looks like this, that tells you the work is the integral of force over distance. So in this case, it's just P and delta, right? Because that's exactly what we're doing here. So the integral of force over distance is our definition of work, and so therefore the work done to break this material is nothing more than the area under this curve. And so now we can see if we have a brittle material, even if it has pretty much the same slope, and even if it went up to the point where the yield point was similar for the brittle material and the ductile material, it would still fall at a point like that, and so still quite a bit less area under the curve. So why is the area under the curve important? Well, what are the units of work? So work has the same units as energy. So work and energy are the same thing. And so if you think about it, if I have an object and I drop it from some height, it's going to hit the ground with some amount of kinetic energy. Now, if that kinetic energy is greater than the area under this curve, then you can imagine there might be a tendency for the thing just to shatter and fall apart. Whereas if that kinetic energy of the object hitting the ground was much less than the area under this curve, it would be very difficult for the object to shatter. Now in this diagram I'm showing P versus delta. In the previous diagram I showed stress versus strain. But let's just think about what the integral of stress versus strain is. So if I integrate stress d strain, that's the same thing as our load P, or our force, divided by the area. That's the same as stress. And strain is our change in length dx divided by the initial length of the bar L. So if I write this, this is 1 over the area of the bar times its length times the integral of P dx. So this is work. 1 over area times length is 1 over volume. So the integral of the stress-strain curve is the energy or the work per unit volume. So we often call this value the strain energy density. So now let's look at how this plays out. So here's a piece of aluminum. Here's a little piece of glass, so a glass slide. A little hard to see on the video, of course. If I take the aluminum, of course, I can bend it past its yield point so that it's nice and ductile, so I can bend this any old way I want. Now the thickness of these two is the same, even though the shape is different. But as you know, the glass, and so you see the glass is quite brittle. It didn't take very much to hit it, and it just shattered. To drive the point home, let's consider the following very simple structure where I just have a bar hanging here supporting a load P, and I have two candidate materials to make this out of, the red one and the blue one. So here we know that the stress is going to be nothing more than the load divided by the area. So if force were the only thing that matters, well, I could for the same load, I could afford to use a smaller area if I were building out of the red material than the blue material, because for the blue material I'd want to not exceed this stress, whereas for the red material I need to stay below that stress. Right? So for the blue material I want to stay below this value so that the bar doesn't permanently deform. For the red one I want to stay below this value so it doesn't shatter. However, force isn't everything. Energy matters too, and energy is the area under the curve. So when I look at the area under the curve, the blue one is significantly greater than the red one. And so what that means is that if I just have a load sitting here hanging nice and still and everything is nice and quiet and static, the red one would in fact probably be the better material. However, if this were made out of a material like glass or a ceramic that was very brittle, represented by the red curve here, if I came along and tapped it or knocked into it, a little bit of impulse of energy could exceed what it could store and it would fracture and break. Materials such as the red one here don't fail because they can't withstand the force. It's because they're subject to breaking with low impulses of energy added to them. Now, of course, when building real structures, there are other requirements that matter. For example, we build our windows out of glass so we can see through them, so we take the risk that someone might throw a baseball through it. Windows made out of metal aren't particularly attractive. Let's return to our Ashby plots. We were looking at this plot which shows Young's modulus versus strength. Now, while strength is an important property to consider when selecting a material for a given application, it's not the only thing that's important, as we've just learned. So there's a variety of other definitions. An important one is called fracture toughness. I won't get into the formal definition, but fracture toughness is related to the property if a material has a small crack in it. Is that crack going to propagate and cause the material to fail, or will the structure be safe? So if we look at fracture toughness versus Young's modulus, we get a diagram like this. And now we see the metal sitting clearly quite higher on the fracture toughness axis than the ceramics. Now there's a lot of complexity in this diagram that we'll visit on another day. This boundary right here is showing kind of a lower limit, meaning you want to definitely stay far away from this curve if you don't want to have a brittle structure. And so the existence of the ceramics near this kind of theoretical minimum here is why the ceramics are so brittle. And again, this is a log scale, so materials up here are many times more tough than these down here. Now let's look at fracture toughness versus strength. So we have fracture toughness on this axis and strength on this one. And again, while we see a general correlation between the two, we have to remember this is a log scale, and so there's quite a bit of scatter here. And now we see why metals really stand out. They not only have high strength, but they have high toughness. And so if you note here, the materials down in this corner of the diagram, fracture before yield, means that if the structure is built out of something down in this corner, it's more likely to break apart and shatter before it is to plastically deform. Things that are up here are likely to yield before they fracture, meaning they're going to be squishy and they're going to deform or crumple, but they're not going to break into two. There are many properties that are important when selecting materials, and here we've just started to dip our toe into the waters. We'll return to these topics in later lectures, but it's important to remember that strength isn't everything.